In this video, I'm going to discuss about this coordination compounds, the definitions which are involved in this chapter. Yes, let's understand the few definitions. The first one is the coordination entity. Yes. What do you mean by this coordination entity? Let's take one simple example and understand what do you mean by this coordination entity. If I take the example of this particular complex coordination compound, yes, it's nothing but this is a central atom which is involved in this, the cobalt, here the transition metal, and the coordination entity is nothing but the central atom which is surrounded by these ions, uh, which are surrounded by these ions, or the neutral molecules is nothing but the coordination entity. For example, in this, the cobalt, which is a central atom, is surrounded by 3 Cl, which are negative ions, and 3 ammonia molecules, which are neutral. So here, the cobalt, which is a transition, the D block element, has been surrounded by 6 groups here, 6 neutral atoms or ions. So it's bounded to the 6 other atoms, and this is called as a coordination entity. For example, if I take one more example of this cobalt taken 6 times, the coordination entity is cobalt surrounded by 6 ammonia molecules in this case. Yes, this is what is a coordination entity, and a few more examples of this is, if I take this example, this is a coordination entity with a nickel which is surrounded by 4 carbonyls, uh, 4 COs here, and platinum here is surrounded by or linked to here 2 Cl2 and chloride ions and 2 ammonia molecules which are neutral. So this is what is the coordination entity. And next comes to the second term, that is the central atom or the ion. If I take the same example of this thing, here the cobalt is surrounded by 6 ammonia molecules. So here the cobalt is the central atom, the atom which is surrounded by other ions or the groups uh, in a definite geometrical manner. So this is what is a central atom. In this, the cobalt, and if you take this, the nickel, here platinum, and here also cobalt. This is what is the central atom. And the central atom here acts as a Lewis acid. So what is a Lewis acid? This Lewis acid is nothing but it's able to accept the electrons. So accept the electrons. So the transition metal here, this cobalt, is able to accept the electrons. So act as a Lewis acid because of presence of incompletely filled d orbitals. It can accept the electrons. You know this already. So these are referred to as a Lewis acids, and which can accept the electrons from these surrounding ions or atoms. Next one is the ligand. So if I take the same example of this thing, here the central atom is surrounded by the fixed number of ions, neutral ions or negative ions. In this case, it is ammonia, which is a neutral, and this is called as a ligand. So ammonia here is acting as a ligand. So there are 6 ligands which is surrounding this central cobalt atom, and this is a neutral molecule and which can donate the electrons towards the central atom. So they are acting as the Lewis bases. So which is able to donate the electrons is nothing but the Lewis acids. So this ammonia, that means the ligands are donating the electrons, and the central atom is accepting the electrons here. So these are acting as the Lewis bases, that is the ligands, and the central atom is acting as what? Lewis acids, that means accepting the electrons. And there is one more term which is used for this ligands. It's also called as the coordinating entity. This is a coordination entity, and these ligands are called as coordinating entity, coordination entity and coordinating entity. In this coordination entity, these ligands are called as coordinating entity or donor atom, because it is donating the electrons towards the central metal atom, or it is also called as the ligating atom. Yeah, these are the terms which are used for the ligating atoms, right? And there are different terms which are used for this ligands. There are different types of ligands. The first one is a unidentate ligand. So the name itself, we can know what is this unidentate ligand. So if I take, for example, the ligand Cl minus or Cn minus or SCN or Br minus or whatever the negative ions I'm taking here, these are having a single donor atom. That means in Cl minus, this itself is donating electron towards the central metal atom here. And so I'm taking the example of this particular thing where with Cl I can take, yes, yeah, Fe Cn taken 6 times 3 minus. So this cyanide ion is having a single donor atom. These are having a single donor atom. So it is acting as a only one donor atom, or called as unidentate ligands here. So these are all unidentate ligands example where they're having the single donor atom. This is donating the electrons towards the central metal atom. So they're acting as Lewis bases, as already discussed. So this is a single donor atom. And next one is if it can be unidentate or polydentate. Again, polydentate means what? It's having more than one donor atom, is nothing but polydentate ligand. So more than one donor atom. So for example, if it can be, bidentate or didentate, tridentate, tetradentate, pentahexa. Okay, so we know that if it is a bidentate or didentate, which means that it has two donor atoms. So if it is having, so in the coordination entity, if the ligands having more than one donor atom, then it is called as a didentate. If it is having three donor atoms, it is called as tridentate. If four, it is called as tetradentate. Five, pentadentate, and six, it is hexadentate. So let's take the examples of each one of these now one by one. Yes, if I'm going for this uh, didentate ligands, that means having two donor atoms, that is the coordination sphere, the coordination entity, if the ligand has two donor atoms, then it is called as didentate ligands. Okay, for example, if I'm taking this ethylene diamine, which is represented by En, this is ethylene, diamine, which is having two donor atoms. So this is the structure of ethylene diamine. So where are the two donor atoms in this? Now this particular ligand, lone pair, this is NH2, this is lone pair. So this is having two donor atoms like this. So this is a didentate ligand. So when I take the example for tridentate ligand, and some more examples for this are carbonate, Cr3 T minus, CO3 2 minus, and glycinato also it is there. Yes, and for tridentate, if I'm taking the, for example, for tridentate, it is diethylene triamine. Yes, I can represent this by di-N. Done. So if I take the structure of this, CH2, NH, it should have three donor atoms, right? So I'll show you the three donor atoms for this. So this nitrogen having the lone pair will act as a donor atom. So yeah, see, 1, 2, and 3. So 1, 2, and 3 donor atoms. So its name is tridentate ligand. So diethylene triamine is a tridentate ligand. When you go for the example for tetradentate ligand, so I can take the example of triethylene tetramine, or I can take nitriloacetate also. So this one is CH2COO minus, CH2CO minus, CH2COO minus, C. 1, 2, 3, and lone pair on this, 4. 4 donor atoms which are present on this, which is nothing but nitric acetate. Okay, so this is a tetradentate ligand which is having 4 donor atoms. So when I take an example of this hexadentate ligand, so it should have 6 donor atoms. Hexa means 6, and the very famous example EDTA. So do you know the full form of this EDTA? Yes, this is ethylene diamine tetraacetic acid. Yes, ethylene, EDTA is very famous. Diamine, ethylene diamine tetraacetic acid. Yes, EDTA, which is having 6 donor atoms. Let me write the structure of this, then it will be clear for you. Yes. CH2 tetra. See, 4 should be there here, 2 on each nitrogen. So all these are acting as, yes. So I should write the other way here. Yeah, let me write this. Yes. CH2 COO minus. So here lone pair, here one more lone pair. So 1, 2, this oxygen 3, 4, 5, and 6 donor atoms which are present in this. So it's a hexadentate ligand. So let me tell you what are ambidentate ligands now. So ambidentate ligands. Yes, you must have heard about this, but still. So ambidentate means it is having 2 donor sites. For example, if I'm taking NO2, so it can act as a donor atom either from this nitrogen side or this oxygen side also. It can act as a donor atoms. That means it is having 2 sides, but only one of them will act as a donor atom at a time. So those are called as donor atoms, which are having 2 possible donor atoms. Thereby it can coordinate with this metal atom from any side of this depending upon the conditions here. So such a ligand is called as an ambidentate ligand. Yes. Now let's coming to the next term, which is coordination sphere. Yes. Coordination sphere. So if I take an example of, yes, the same one, CONH3 taken 6 times. So the coordination sphere is nothing but the central metal atom, which is surrounded by the ligands, which is enclosed in the square brackets. Very simple. This is a coordination sphere. One more example, this one. Yes. C2O4 taken thrice with a charge of 3 minus. This is a coordination sphere. So what is the coordination number now? Since we have understood the coordination sphere, now the coordination number. The coordination number is nothing but the number of the ligands which is surrounding the central metal atom. Or we can say that the number of bonds which are having the central atom with the ligands here. So it's nothing but the number of the coordination bonds. In other words, it is the number of the coordination bonds for the central metal atom. For this, it is the coordination number is 6 surrounded by 6 ammonia molecules. Here also it is 6 because C2O4 is a bidentate ligand, right? The bidentate ligand or a didentate ligand. So it is surrounded by 3, but having each one is having 2 donor atoms. So 2 into 3 is equal to 6. So the coordination number for this also is 6 here because it is a bidentate ligand. Yes. And next is coordination polyhedron. Yes. Coordination polyhedron. So I said, if I take the same example again, this central metal atom is surrounded by six metal ions, I mean, six ligands, and is enclosed in the square brackets, which is the coordination sphere. Now, this ligands are attached to this central metal atom by means of particular geometry. That's a spatial arrangement is possible. A particular geometry is possible for this. So, the possible geometries for this particular thing, where I'm taking this is an octahedral. So, but it can be so octahedral. You know the structure of this. So it is something like this. So it's surrounded by six ligands. Yeah, this is all four ligands in one plane, and this is above and below the plane. So this is this arrangement of the ligands around the central atom. So this, in this case, it is octahedral, and it can be tetrahedral, square planar, or square pyramidal, or whatever. All everything is possible depending upon the hybridization which is possible in it. So it can be square pyramidal or trigonal pyramidal, bipyramidal. So let us discuss a few things here, a few of the geometries here. So if I take the example of tetrahedral geometry, that is possible for nickel here with CO. So the geometry which is present in is tetrahedral geometry. So tetrahedral, so it's tetrahedral, you know how it is linked. This is the tetrahedral geometry, right? And the other which is possible for PTCl4 2 minus the geometry which is seen is square planar here. So how does the square planar look? I'll show you. Square planar here. So this is square planar. All arranged in one plane here. This is what is square planar. So there's a different, this is what is the polyhedron, coordination polyhedron. So that means the spatial arrangement of the ligands which are bonded towards the central metal atom is nothing but the coordination polyhedron. And this is trigonal bipyramidal. The three of them in one plane and one above and below the plane of this is nothing but trigonal bipyramidal geometry. Yes. This is what is about the spatial arrangement. And next one is the oxidation number of central atom. So the central atom here will carry some charge. So that is what is the oxidation number of the central metal atom. For example, if I take this nickel, so what is the charge on this? CO is neutral, so nickel will carry the zero charge here. If I take this one, sorry, this should be enclosed in square brackets, right? So let me write it again. PTCl4. Yeah, so what is the charge on this complex? It is 2 minus, so this is 4 minus. Since the charge on this is 2 minus, should be 2 plus. So this is how you calculate the charge of this central metal atom. This is platinum is 2 here. So it should be enclosed in a parenthesis. The charge should be written besides this central metal atom. Yes. If I take an example of cobalt, ammonia, taken 4 times Cl2 plus. So what is the charge on this cobalt, the central atom? How to calculate this? This is 0, right? This will be -1, so total will be -2. Since the charge on this square bracket is plus, so this should be +3, right? So it should be written something like this. So these are the few terms which are involved in the coordination geometry.